Yo, what's up, guy? Okay, today we're gonna solve uh the daily question on Leetcode. And today we got a hard problem. That's this find the maximum number of fruits collected. All right, let's just read out the statement. Um, this game tangents comprise of okay. You are given a 2D array fruits, psi and where occurs number of fruits in the room. Alright, three children will play in the game dungeon with initial positions at the corner room. Mm, three corner 0 0, 0 9 0 the last wheel, and the position here the sorry, this two corner, this this and this. Okay, all right. Uh, so the children will make exactly one and minus one moves. Hmm. Uh, according to the following rule to reach the how can this reach to this with n? Just check it out. The child starting from 0 0 must move from their current room to one of the rooms a plus one and tray plus one. That means the diagonal here. Diagonal. Actually, diagonal. Diagonal.
diagonal,
Diagonal. 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 And e plus one tray and e equal you can, this means you can move to three neighbor, the left, the bottom, and the diagonal. And the to start from 0 minus 1 to move to e plus 1, this j plus 1, and I plus 1, okay, or I plus 1, j plus 1, that means the three cell below it. And okay, we start I minus 1 tray plus 1, that's this diagonal, and I minus 1 and tray plus 1, that's a oh wait a minute, that's the diagonal, and the diagonal on the right, the left side, and go up, that's it. I'm sorry, I and tray plus 1, that's a go to the right. I plus 1 tray plus 1, that's equal this diagonal to the right side, and I minus 1, that's it, and 3 minus, oh sorry, that's it. Okay, here that the three cells on the right side of the third child. So when a child enters the room, you will collect on the fruits there if two or more children enter the same room, or only one children could collect the fruits. Okay, understand about it. So our task is to return the minimum number of fruits the children can collect from the dungeon. Really hard question, man. So to summarize this, we got a room full of fruits and times n, and we have three children. One start here that can move to three cell, to the left, to the right, to the bottom, and to the diagonal on the right side. The second child could go to three cell of the below of the first. Let me check the first again. E plus one, j plus one, a plus one, I plus one. This I and j plus one. That's right. And the last child go to the three. Could go to the three cell neighboring. That's the three cell on the right side. This. Okay, understand. Understand it. So because make exactly minus one moves. Exactly, remember the word exactly. Okay, and a child will collect on the fruits when entering a room. Collect it, then it become empty. So there's no to try could collect the same fruits in the same room. Okay, understand. So just draw the first example here. 1, 2, 3, 4, 5, 6, 7, oh, 8, 7, 1, 10, 11, 10, 9, 13, 14. What did I so? Okay, we got this room. Change the color, and we will start from this room, and this room. So the first try will move like from this to this to this to this. So that's exactly n minus one. Oh my god! To make exactly n minus one, so the second try from this go to one two one one two this and two three this and this. Oh, that's right. Mm. And this try is gonna go like this, this, and this. Oh, okay. Understand the constraints. 1,000. Okay, really reasonable. And okay, we need to think a little bit here. Uh, so we got some opposition. Gonna talk about some opposition. First of all, the first try, the shortest path you can move from a cell, the the this corner, that is the left and upper corner, to this to the destination. You can move to the left or the right. You must only way to move in the diagonal. Why? You got n minus one, so the shortest path from this node to this node is go in the diagonal, and the shortest path is exactly n minus one, because there are n minus one cells on the diagonal from 0, 0 to n minus one, n minus one. 1, 2, 1, 2, 3. That's it. If you move to the left, okay, if you move to the left, that means you need one move to the bottom, right? You want to move to the bottom because um, actually, if you choose to move like this, mm, let me see how to put it best. So if we move to the left side, that means we need to go down. We need to go down somewhere. If you choose to go to diagonal on, so the final you reach the edge, you not reach the destination. You sort of need to go down for sure. Um, it's the same case as you go down. So yeah, there's obvious the sort of path go directly to the destination. So it costs you n minus one, and there's no other way. If you move to this, that means you choose to move this. That is short path, and it costs you extra. So the maximum way you can move is like n plus n minus 1. 1, 2, 3, 4, 5, 6. Sorry, minus 2. That's the maximum way. And this is the minimum way. So somehow there's only one way for the first try to move, that is through the diagonal. So through that, I just prove it. Just move the diagonal. The first try is done. You just go toward to the destination. How about the second try? It can move to anywhere. It can go directly to this, and it only take is n minus 1 exactly. Okay, I can see. So just for demonstration, start from this. You can go to this, the layer 1, imagine using BFF algorithm. Uh, so the next step you could move to on cell like this, right? Is the one zero step. It costs you one step. This costs you two step, and so on. So you could reach anyone in this layer for actually the so it means you could reach. So it's just depends on the distance. I mean the actually the height. Okay, the height is it like 4 and this is 1 2 3 4. You could reach this by go through this or go through to this or go through mm, okay reach this with 4, but actually you could reach it with 4, but uh the best way is to 1 2 and 3 9. So the range the range to get this is go straight, go to the left one. So you could go back, you still in range, you could go back. But if you go outside, that means you cost you one extra step in order to go back, right? You go back from this position, you need to go somewhere and back to this position for sure. You could go like this, but you must back to this and go directly to this code you exactly n-1. But you could go to one, go outside, go to the left or to the right one step. Why? Because you could go back easily in one step. But if you go back, go out 2 step, you need one step to back. You need 2 step, and you mean that's it. You goes 1 step here and 1 step to the, the same row, same column. So you could only move to outside to the left or to the right one time. So you could move like this. You could go this and go this 2 step, and you need one more directly. Oh my god. Sorry. That's okay that you couldn't move to the left to the right side. Wow. Should let me try it again. Well, so you can move it, so you just can move to the left when the space at least 2. Let's draw more. But we don't care about this. Okay. Mm. Take the color red for sure. Uh, you can go from this to race, then but you can't, right? So the the step you can go to the left or the right is it must be far from the destination 2 step. So you could go from this, you can go this, that's easy. You could go this, easy. Just go outside one and make sure you don't go outside at the n-2 for sure. Okay, that's the second solution. So it's like you could go something like this, sure. And the same case as the third try, you could go up or go down in one short step. So there are 3 things. First try, the first try can only go in diagonal. What? Diagonal? So sorry, but diagonal. Okay, diagonal. From straight. That's it. Second is opposition here. Okay, observation. The second chart. The second chart could Sure, for sure, right? 0, this is 3, this is 2. You can go from this to just one from minus 3, that's the 1, 2. Sorry, it must be 3. Sure. You can go to this, to the right. Okay. So the step is like straight, left or right, straight, and then right or left, right versus and straight. This is optional, optional, optional. This is always optional. Got it. So the problem is now need to optimize the codes. Yeah, I want to remove this to try this again. Sorry. That's messy, so I decide to delete it. Right. Okay. The destination here, here, and here. Just go directly, and for sure you're gonna gain all of this. So this can only this. So I believe that the maximum way let the first try collect on the cell from this diagonal. For this try, you could go choose somewhere to go left or right. You could choose this, right? So I would try H. I would try H. You can go this. You can choose to go left at the 0. You can choose to go left at the 1, and then you will choose the position where you go to the right. That's 2 position. Remember. So with that, you could maximize the range. The range of this is somewhere cover this, and the range of the the this tribe maybe cover this, so it will meet somewhere on the diagonal, and our task is try to maximize this somehow. uh, so I love to draw it larger. So you just for the first go straight to the source destination for sure. Second, for example, here you can from here to go to some left position to go. Sorry, not exactly one. I just figure out I was wrong for my assumption. So that assumption is not true. So from this you can go there and you can go there, right? That means the boundary is exactly m divided by 2. Because when you move to the left, you have a trend to move to the right, and that must be some must be zero. Zero. That's you go left two, you must go back two. So it must be as maximum n divided by two. One, two, three, four. You get 4 steps here, and that exactly 2 divided by 4. But if exactly n divided by 4 lower ceiling flooring. Wow. Wow, it's really interesting now. How could I manage this? Wow, this would go like this, right? And this guy could go like this. Like, so I think we need to like try the best to prevent them meet each other, while still maximize the sum. Okay, we know the range this guy can reach is somewhere. This is really maximum one, and the actually this is really maximum one too. Somehow it will meet somewhere. Wow, man, this real hard. How could we do achieve this? Well, and power and solution. If we just use DP, this is so easy. This guy can uh, go this, then go one, two, 1, 2, 3, 4, 5, 6. 1, 2, 3, 5 only. 1, 2, 3, 4, 5. That's it. 1, 2, 3, 4, 5. That's it. 1, 2, 3, 4, 5. No, no, no. Let me go back somewhere to this. I think it's really hard. Mm. But check figure out. So we could calculate on the optimal solution. For example, you could calculate the optimal solution to reach this position, and make sure this on zero. For sure, you need to make it on zero because we want to maximize the first try. It's there only one way for them, but for the second and the third try, you can go anywhere. Uh, so my solution is I let the first try go straight to the source, to the destination, and calculate the optimal solution for each cell. So I'd love to go to this and how to avoid, uh, you know, to detect the collision. That is try to figure out let the third try go somewhere reach to this or reach this. If it reach this, that means it can reach this for sure. The third try, okay, and so if it reaches, it may reach this, but if it reaches, it can. So I love to make it reaches. So somewhere it's go to this in mass mind, and let the second try go to this, and after that the third try must go somewhere be here, right? Oh, mm. go somewhere here or go somewhere here, but it may be collision a little bit with distortion. So it's like we're gonna figure out two things. The first step, I love to believe it. Okay, so we for the first the second try, and the first try may go from this to this way. Sorry, H go from this to this for sure, and the second try could the first try could go from this to this or to this wherever. So for this position, I'd love to check out if the second try could go from this to this, so we could go to this and this without any collision. For sure, this is always collision, always, always. Um, so mm, just get the maximum weight from this to the because can't reach anymore, and same at this, right? No, no, no. My idea is to figure out each index. Let's check another example. For example, you go to this position and you could go to this position for sure, and you could choose this or this. And the second is you can go from this to this only, and this maybe. So for the solution, you go to the left side, and this guy go this. The optimal solution is you can go to this, but just some um well this actually if we go to this we can to consider if it will meet again. How could we do this? This problem is really hard, but I think there's something we could do. Go from this to this, go this. So it may do something like this. Just I want a hint to solve this problem. Oh no, I know this. Sure, for real. I know it can reach. Oh, but I just talk about this. Well, now it will not intersect, but will have to share an edge, right? It will intersect, but it will share have a certain edge. This and to this. Sure, it will have certain edge to go to this. You must go down here. If, for example, you go like this, well, this is the battery. You can go outside that. You cannot go outside the battery. This is the battery, and you can intersect it somewhere. For example, you reach the value, can only go down. For sure, you can only go down. You can go forward because out of reach with the diagonal. Mm. So for this case, you can only go through back to this. You can go down. You can go right. So the solution, the solution is simple. So I will find on optimal solution to a position, and yeah, it's in the safe zone like this one. On the safe zone, you may you may fill out this. So it on the edge. So consider. So I will consider the second try. It could go from this to this. So that means zone is filled out on the index they could read. But so just calculate the solution and create the DP1 uh, for the second try, and the DP2 for the third try. That's the actually initially is on 0. Yeah. What's my place? Yeah. With a hint, we could solve it now. Ah, it's just a hint, but I couldn't figure it out, so it's uh, need the interviewer have. Okay, now calculate the dB for in range. Uh, this one can go somewhere from the solution, go somewhere. This for if range from then and actually trade n plus 1 to 0 is minus 1 and TP1 I trade. We actually f I is larger than 0. I change like max I change which like p minus 1. It go from the top, go from the top, right? Plus first I trade if trade less than 1. I trade I trade. Okay. Yeah, we could just can calculate from the first actually dp 0 and minus 1, the actual plus 0 and minus 1. Okay. So we could ignore this. Just to make sure, okay? Just to make sure. J to I minus 1 plus I J and actually if J is less than, so we could do this one, so do something like J plus I J minus 1 J plus 1 plus I J, that's it. So for the stripe, we're gonna go from the bottom here, minus 1, minus 1, minus 1, trade increasing to the end. So we could go from 1 for sure, and make sure the TP minus 10, so it actually push minus 10. That's it. And the TPI trace, mass TPI tray with TPI. Actually, this is the I plus tray minus 1 with push I tray. If I trace, actually, if the I is less than 0, so TPI tray is a mass of TPI tray with the TPI. So minus 1 plus push I tray as well as case I. It's like we need to go through a column, not the. So it might be like that. Yeah. And this one, so we could do something like ij like TPI plus 1. That's the. You could go from this to this. Plus 1 plus ij. Sure. Yeah. Got it. So print it. No. DP1. That is DP1. In order to check it, only check to be sure. Don't forget to calculate. Uh, calculate. Okay. This case is 4. Make sure if you go out, you can go back. That means we need to store. You can only go to this diagonal. So change is right down to exactly I. This one. Right? Okay, that's right. That's really right. This is on 0. Okay, 0, and this line is. Uh-huh. It's just okay, but we need to calculate someone you go from person to the end. So, oh my god, calculate dp again. Oh god. So lazy to blame the solution guy. Wow. But I think we should do this somehow. It's a really long solution. I really don't like this problem. It's really long. This god is actually not good somehow. It's really not good. Well, I think we could go to work somehow. So boring. Oh, it can't reach. Oh man. Yeah, it not intersect each other, so just get the mass. What I done? What I done? Oh, I see. So I think the problem. I think this is assigned to really large number. Why? What? The man is here. Silly, silly. This happy simply ignore the case. That's not reachable.